Now that we have established that there are boundaries between the different uh, spaces, so you have the kernel space and the user space. In many cases, the user actually requires to touch the hardware, because, for example, you want to write to disk, and you do not want the user to take full control of disk, but you want the user to be able to write to disk. Similarly, if you're reading and writing to memory, because, well, this is a very common operation that you will have in your system, you load some variables in your memory, you operate on them, you store them in memory, and so on and so forth. So you cannot allow the user to again touch the memory on his own. So the way that this is done is that the operating system provides to the user system calls. These are basically operating system procedures. They are just like operating system functions that executes some privileged instructions under the supervision of the operating system. So this is an API exported by the kernel, and it differs from kernel to kernel, as we'll see. When you call an operating system procedure, you call something called a trap. A trap is basically sort of an interrupt to the processor, to the operating system, that tells the operating system that now there has been a system call from the API, from the application level, that requires you to do something, that requires me to do something as an operating system. When you cause a trap, there are predefined procedures in the kernel that basically handles the trap. So what happens when I call the system call open, which opens a file descriptor? What happens when I call the system call close for a file descriptor? What happens when I do a write? There is a procedure. There are like multiple steps that the operating system has to do, and these are all saved in a trap vector. And the vector basically has name. You can view it as that. You have a name of the system call that just occurred, and what am I going to do as an operating system? The trap handlers uses the parameter of the system call to jump to the appropriate handler, because you might have different parameters that might change the way that the trap handler slash the procedure that is required to be done is done. The trap handler saves the caller state, so it basically saves the current state of the system, where what was the system doing when it got this trap, basically. So that once this trap is handled, this procedure is handled, you can go back to whatever it was doing. Okay? The architecture must permit the operating system to verify the caller's parameters. So you basically should be able to verify that this is kosher. This is something that this user program can actually do. And the architecture must also provide a way to return to the user mode when finished. Because once you basically call a system call, you go back, you basically go to the kernel mode, you check as a kernel, you check as an operating system if this is fine to do, if this operation is permitted, and if it's not, then you basically raise an exception. Otherwise, you execute the system call, basically execute the trap handler, the procedure, and return from the system call to the user. These are some example system calls. We'll actually cover some of them. For example, one of them is fork, which creates a child process identical to the parent. It basically creates a new thread. You can view it that way. Uh, you can wait PID, which basically waits for a child to terminate. So basically, you can start a new child that will do something new, and then you wait for it to terminate. And there are multiple such system calls. There are some of them, these are some that are process management, some are related to file management, and so on. These are the Windows system calls. As I was saying, there are different system calls for different systems. So these are actually system calls for Linux. These are the Windows system calls. Some of them have the same, well, most of them do not have even the same name as the Unix system calls. This is a complete list of the Linux system calls. Windows has not been doing great when it comes to basically exposing this their system calls. So some people have tried to reverse engineer it, and these are some of these. Okay, of course you're not supposed to memorize them or know what each system call does by heart, or what is the difference between Unix and Windows 32. Unix is basically all Linux flavors. But I mean, you just should know that there are different system calls for different operations in the different operating systems, and you can actually see that even some of them exist for Linux and do not exist for Windows, which is like change mod kill. I mean, there are many of these that will exist for one operating system and will not exist for the other. So let's go back to the idea of protection. Now we have established that there is a kernel mode, there is a user mode, and this way the operating system can actually provide protection in the sense of basically what operates on what. So if you're in kernel mode, you do kernel mode instructions. You can do all sorts of instructions, everything you can do. If you're in user mode, well, you're limited by whatever instructions are permitted in that mode, which is different from different operating systems, and by the system calls that the operating system provides you to do some hardware related operations. Okay. Now we come to memory protection, where the architecture must provide support so that the operating system must make sure that, well, no application is capable, for example, to read memory from other applications, or no application is capable of changing the operating system code, for example, because everything is in memory now. So the way to do that, and the simplest way that hardware and operating systems support such memory protection, is using the base and bound, or base and limit registers, where you basically limit an application by a base register. Each application will have running in memory will have a base register and a limit register, which basically tells the operating system and the hardware that this application is only allowed to operate within this region of memory. It's not allowed to, for example, do anything in this region of memory. And the CPU checks each user reference to memory if it's within this region or if it's trying to access something else. So who changes the base and bound registers? There is an abstraction that we need to actually talk about. I mean, here we talked about job 1, job 2, job 3, job 4. I mean, different applications. Here we are going to talk about the process abstraction. A process is basically an operating system's abstraction for executing a program. It's basically your program. Okay, so each program can be a single process or multiple processes. We'll talk about that later, but basically you're trying to limit a program to some areas, and this is done using the process abstraction, which is very common in almost all operating systems. A process needs permission from an operating system to access memory that it was not allocated to, and before writing to disk, before accessing other hardware, and so on. The abstraction needs to allow the program to run with good performance. So you should not limit the program performance by abstracting using your processes. So this is, again, one of the main aims of operating systems. A process has this layout in memory. Typically, you'll have stack. The stack is basically where you have the program code, you'll have some data, and you'll have some text. But actually, they are not even called stack data and text. They are actually, you have them, a typical process will look like that. Actually, you have the source code, you compile it, you get an executable image with instruction and data. This is basically what compilers do. You compile it and you have a software that is compiled, like our CPU.c program. Then when you load this program in memory, you load it like this. You have the machine instructions. These are this is sort of all the instructions you have for the machine in this program. You have the data that the machine that the program is going to operate on. For example, in our CPU.c, this would be your arguments, the arguments that we provided, the letter A, the letter B, the letter C, the letter D, and so on. You have some data that you can operate on. You have the heap, which is basically any dynamically allocated data structure that the program needs. Suppose that, for example, you take an input and you do operations on it. So suppose that you take from the user a string, a long string, and you do multiple operations on the string. You concatenate it, you cut it, you split it, you do different things. So you store such data in your heap. Okay, this is sort of dynamically allocated data structure that the program might need. I mean, if you have a linked list, for example, where do you store it? You store it in the heap. And then you have the stack, which is basically, it's where you hold the local variables of procedure calls. So you jump between different functions in your program. All of us have programmed something, and when jumping, well, these jumps basically, you have you have all your local variables in the stack, and then you might have multiple applications running. So one central thing in operating systems is that you load the first process, you load the second process, and you leave a gap in between them. And this gap is not a physical gap. It's not like you're not really using your full memory. You're actually going to use your full memory, but this is a virtual gap. This basically means that the instruction, the memory name, and the way you basically give names to different memory parts will have these gaps. So you'll create gaps as you load memory. So here's a question: can base and bound registers grow? Base and bound basically are the ones that confines a program to a certain part of the memory. So can these change? So now we have talked about privileged instructions, where basically only the kernel can run these instructions. We have talked about memory protection with the allocation, and there's what we call the timer interrupts. Basically, the kernel must be able to regain control of the processor at any time. This is again a protection. Why is this a protection? Because basically you might end up with a situation where one of the programs is going into an infinite loop. It's never basically stopping. So the kernel must be able to force this program to stop, to give processor time to other programs. One thing that we have been talking about a bit are registers, and registers are basically it's dedicated name for one word of memory managed by the CPU. So you have your normal memory, your normal RAM, but then the CPU itself has some memory, which is typically called registers. And these include, for example, the base and bound registers that we were talking about. This is where the processor stores the base and bound registers for an application, for example. Okay? You have the stack pointer, which basically points to where you're reading from memory, or basically what instruction you're basically running now from the program. You have the program counter that basically tells you where you're going to go next to fetch the next instruction.